Welcome. In this video, we're going to verify that each field below is conservative. And now recall that if you have some field, let's just say f is equal to a comma b, what you want to verify is the partial of a with respect to y is equal to the partial of b with respect to x. And this is the case in 2 dimensions. So this is the R2 case. So in this case, a is y squared. That's our a. So let's go ahead and find the partial of a with respect to y. That is the partial with respect to y of y squared. Well, that's equal to 2y. All right, now let's do the same thing for b. And that's 2xy. So the partial of b with respect to x is the partial derivative with respect to x of 2xy. That's just equal to 2y. Notice that these are equal to each other. So these are equal. So let's write out a sentence. And you might not have enough space in your notes, but definitely just squeeze it in the margins or use a Post-it note. Those of you writing digitally can easily make your space larger. Since the partials, that is the partial of the x component, which we called a in our case, since the partial of a with respect to y is equal to the partial of b with respect to x, f is indeed conservative. All right, now let's look at b. And pardon me, I'm going to definitely make some space. There we are. So now in the 3-dimensional case, which we have in part b, we just need to evaluate a little bit more on partial derivatives. We have f is equal to a comma b comma c. So we need to verify what we did last time, which is the partial of a with respect to y is equal to the partial of b with respect to x. That's the first one. But then we also need to verify that the partial of a with respect to z is equal to the partial of c, that's our z component here, with respect to x. And then we have one more. We have to verify that the partial of b, our y component, with respect to z, is equal to the partial of c, the z component, with respect to y. So let's verify all 3 of those. So let's start with this one. So the partial of a, that's this one here, the first component of our vector field, the I component, the partial of a with respect to y, well, that's equal to the partial with respect to y of 3x squared plus 3y squared. And now with respect to y, this is just a constant, so that's 0, and this will be 6y. Now let's look at the partial of b with respect to x. That's the partial derivative with respect to x of our b component here, which is 6xy. Well, with respect to x, this derivative, x becomes a 1. 6 times 1 times y is just 6y. These match, which is exactly what we wanted. So we're done here. And here's a check mark to show we're done. Now let's verify this condition here. So we're going to look at the partial of a with respect to z. That's the partial derivative with respect to z of 3x squared plus 3y squared. Well, both of these are just constants with respect to z, so this derivative is 0. Now let's look at the partial derivative of the z component, which we call c in our case here. the C component with respect to x. That's equal to the partial with respect to x of 4z cubed, which is equal to, again, 0, because 4z cubed with respect to x, well, that's just a constant, so 0. And again, these match. So we verified this second condition. We have one more to verify. Okay, as you can see, I made a little more space here so we can do number 3 here at the bottom. And as we can verify number 3, we can verify the partial of this b component, that is the y, the second component here, with respect to z is equal to the partial derivative of the last component, c, with respect to y. So that's what we're verifying here. And actually, I should stick to how I've been doing these. So let's go ahead and put these separately here. So the partial with respect to z of that b component, which is 6xy, well, there is no z here, so that's just 0. Now, the partial with respect to y of that c component, which is 4z cubed, well, again, this one is also just 0. Now, finally, these also match. There we go. I'm going to give all these happy faces since they match. So we're done. So since all the partial derivatives, these ones here, match, we know this vector field is indeed conservative. So since the above 1, 2, and 3 partial derivatives match, we know that f is indeed conservative. Or we can write a conservative vector field. Please keep calm and math on.